Hi, hello, dear all. Welcome back to the class on rotational dynamics. In the last class, we have seen how we derive the expression for the moments of inertia of some regular bodies. So we are continuing that. So we have already derived moment of inertia of a ring, moment of inertia of a bar or a rod. So we have seen such bodies. So the topic of today's discussion is how we will calculate the moment of inertia of a disk. So as we have already done in the earlier classes, we will take different axes. For example, if I am considering a disk, I have drawn the picture. I am considering a disk like this, and the axis that I am going to take first is an axis passing through the center of this disk and perpendicular to its plane. Plane of the disk means it is in this plane. So perpendicular to the plane, passing through the center means I am considering an axis like this. Okay. Then I am going to find out the moment of inertia of this disk about this axis passing through the center and perpendicular to the plane. അതാണ് നമ്മൾ ചെയ്യാൻ പോകുന്നത്. So നമ്മൾ നേരത്തെ ചെയ്ത പോലെ തന്നെ as you have already done in the case of other objects, we are considering first a thin circular disk of radius r with center of. So we are considering an axis passing through the center, that is PQ. Now, in order to calculate the moment of inertia of this disk about this axis, first we will consider a small portion. That is why we are taking like this is because of this disk. We have already calculated the moment of inertia of a ring. Now we can assume or we can consider that this disk is made up of many rings. For example, I can say that this disk is made up of a ring like this. Okay, and if I join another ring here, it will come here. Okay, and if I am placing more and more rings like this, another ring will come here, another ring of smaller radius, another ring of smaller radius like this. I don't have all the rings to complete this disk, but I have something like this. Okay, I have a smaller one here. So if I place all these rings here, one ring here, another ring here like that, if all these rings are placed together, I will get a disk. So I can say that a disk is made up of a large number of rings of different radii, and we can see that these rings are at different distances from the axis that we are considering. ഇപ്പോൾ ഇവിടെയാണ് നമ്മൾ ആക്സിസ് പറയുന്നത്. ഈ ആക്സിസിൽ നിന്ന് ഡിഫറെന്റ് ഡിസ്റ്റൻസസ് ആണ് ഈ റിങ്ങിനുള്ളത്. So first what we are going to calculate is the moment of inertia of a ring. So I have considered such a ring here of radius x. R എന്ന് പറഞ്ഞാൽ that is the radius of the disk. But if I am considering that this disk is made up of a large number of rings, I am considering such a disk. അപ്പോൾ ഇതുപോലെ ഒരു ഡിസ്ക് റിംഗ് കൺസിഡർ ചെയ്യാണ്. ഇതുപോലെ ഒരു റിംഗ് ഞാൻ കൺസിഡർ ചെയ്യാണ്. So I am considering that this disk is made up of a large number of rings. I am considering such rings like this. Okay. I don't have all the rings, പക്ഷേ ഉള്ളത് വെച്ചിട്ട് ഇത് ചെയ്യാണ്. അതിനിടയ്ക്കൊക്കെ റിങ്സ് ഉണ്ട്. In between there are rings, but so you can see that this disk is made up of a large number of rings, and I am considering such a ring of radius x and thickness dx. അപ്പോൾ ഇതിന്റെ പ്രൊസീജിയർ എന്ന് പറഞ്ഞാൽ ഇത്രയേ ഉള്ളൂ. We have already derived the moment of inertia of a ring about an axis passing through the center. So we will first calculate the moment of inertia of this ring about this axis. അതാണ് നമ്മൾ ആദ്യം ചെയ്യാൻ പോകുന്നത്. എന്നിട്ട് എന്ത് ചെയ്യും? എന്നിട്ട് നമ്മൾ നേരത്തെ ഇതുപോലെ we will integrate that expression. Why should we integrate? Because we have already seen that this disk is made up of a large number of rings. ആ റിംഗ് എവിടെ നിന്നിട്ട് എവിടെ വരെ വരാം? ഇങ്ങനെ ഒരു റിംഗ് വരാം. ഓക്കെ, ഇങ്ങനെ ഒരു റിംഗ് വരാം. ഇതിന്റെ പുറത്ത് ഇങ്ങനെ ഒരു റിംഗ് വരാം. We can have another ring of this diameter, and finally we can have another ring of this diameter. So when we are integrating, first we will find the moment of inertia of a ring about this axis. Then we will argue that we can have such rings from this point to this point. ഇവിടെ തൊട്ട് ഇവിടെ വരെ നമുക്ക് അങ്ങനെ പല പല റിംഗ് ചേർന്നിട്ടാണ് ഈ ഡിസ്ക് ഉണ്ടായിരുന്നത്. So we can say that if after finding out the moment of inertia of a ring, of a particular ring, for example this ring, I can say that such rings are existing from this point to this point. എന്നിട്ട് നമ്മൾ അതിനെ ഇന്റഗ്രേറ്റ് ചെയ്യും. ഇന്റഗ്രേറ്റ് ചെയ്യുമ്പോൾ എവിടെ നിന്നിട്ട് എവിടെ വരെ ഇന്റഗ്രേറ്റ് ചെയ്യണം? So from which limit to which limit? From 0, that means we are starting here 0 to r, that means the radius of the disk. So we can say that such rings are constituting the disk, and the radius of the ring is having a range from r is equal to 0 to r is equal to r. Then we will integrate the expression. So the steps are like this. The first step, as always, is to find out the mass per unit area. In the case of rod, we have found out mass per unit length. Okay, here what we are going to take first, or write the first step. To write the first step, we will go for mass per unit area of the disk. We will take. Then you will take the mass of this thing. Okay. Then you will multiply that mass per unit area into the area. I'm sorry, the area of the ring we will take. Then multiply by the area of this ring will give you the mass of the ring. Then we will, after getting the mass of the ring, we will calculate the moment of inertia of the ring about this axis. After getting the moment of inertia of the ring about the axis, we will integrate this, because such rings can exist from this point to this point. So wide range of radii. So we will integrate. Then we will get the moment of inertia of the disk about this axis. So that is our procedure. So the first step is always to find out what mass per unit area of the disk. I have taken the mass of the disk as capital M, and the radius of the disk, mass of the disk as capital M, radius of the disk as capital R. So what is mass per unit area of the disk? Area of the disk, as we know, is pi r squared, because it is r is the radius. Then mass, total mass, is capital M. So mass per unit area of the disk is m by pi r squared. So here I will write mass per unit area of the disk is equal to total mass divided by its area, it is pi r squared. Now I got mass per unit area. Then I have to take the area of this ring. I am considering a ring of radius x and thickness dx. This thickness and dx. This much thickness is dx. Okay. So what is the area of a ring of radius x and thickness dx? So that is given by area of the strip. I am considering the circular strip. Area of the circular strip of radius x and thickness dx is given by 2 pi x dx. Okay. So that is 2 pi x dx. Now I have got mass per unit area, then mass of the strip. So what I can write, therefore mass of this strip, this circular strip, is equal to, I have mass per unit area in area, just multiply this by this. Okay, I can write m by pi r squared, that is the mass per unit area, into whatever be the area of the strip, that is 2 pi x dx. So this is the mass of the circular strip. So after getting the mass of the circular strip, you go for the moment of inertia of this circular strip. Or circular strip is ring about this axis. So what is that? Therefore mi of the circular strip about this axis pq, that is given by, as you know, moment of inertia is always mass into the square of the distance between the strip and the axis. So what is the distance between the strip and the axis? It is x. Mass number. So mass into x squared. So that will be m by pi r squared 2 pi x dx into mass. This much is mass into x squared, because moment of inertia is mass into square of the distance between the body or the particle of mass m and the axis. So we have taken like this. So what is this? This is to take all the constant from one side. Pi and pi will get cancelled. Then what will you get? Then here I have it. So this is 2m by r squared x cubed dx. So this is what you are getting. ഇനി നമ്മൾ എന്താ ചെയ്യേണ്ടത്? ഇത് ഒരു റിങ്ങിന്റെ ആണ്. This is the moment of inertia of the ring we have considered here about this axis. ഇങ്ങനെയുള്ള റിംഗ് എവിടെ നിന്നിട്ട് എവിടെ വരെ പറയാം? Such rings can exist from r is equal to 0 to r is equal to r. So we have to integrate it from 0 to r. Limit to 0 to r കൊടുക്കുക. So moment of inertia of the disk about PQ is given by mi of the disk about PQ, and we return to be equal to 2m by r squared. I am taking this outside of the integral because this is a constant. Mass of the disk is a constant, radius of the disk is a constant. Integrate integrate 0 to r. 0 to r. That is x cubed dx. So this is, as you know, it is x cubed dx in the integral, it is x raised to 4 by 4. So that will be 2m by r squared x raised to 4 by 4. Integral of x raised to n dx is x raised to n plus 1 by n plus 1. So now applying limits 0 to r. Okay. Apply first this limit, then minus apply this limit. So it will be 2m by r squared into first limit appliement is, instead of x I will put r, that is r raised to 4 by 4 minus, when I am putting here 0 in the place of x I will get 0. So this is nothing but 2m by r squared into r raised to 4 by 4. Okay. So if I am taking this as I, moment of inertia of the disk about I am taking it as I is equal to, so we can say that this 2 and 4 will get here. 2 will come here, r squared and r raised to 4. So what will you get? Here there will be 1 2, then there will be r squared. So what will be, that is mr squared by 2. So this is what we are getting. So what do you understand from this? The moment of inertia of a disk of mass m and radius r is given by mr squared by 2. So about an axis passing through the center. So moment of inertia of a disk about an axis passing through its center and perpendicular to its plane is given by mr squared by 2, where r is the radius of the disk and m is the mass. So now we have considered this axis. We will consider different axes. Now axis, just like we have seen in the case of rod and ring, we can consider this string, this axis. Okay. Now we have considered, we can consider another axis. This, if we know this, we can calculate this. What is the theorem that we are applying? That is parallel axis theorem. Parallel axis, apply parallel axis theorem. If I know this one, which we have already found out, I can know this one. Moment of inertia of this disk about an axis passing through the center, but parallel to the plane, lying on the plane. What is the theorem that we are applying there? It is perpendicular axis theorem. If you know this one, moment of inertia of the disk about this axis, I can calculate this one about this axis as well as about this axis by applying perpendicular axis theorem. അപ്പോൾ അങ്ങനെ പല സാധനങ്ങൾ നമ്മൾ ഇത് അറിഞ്ഞാൽ ഇത് കണ്ടുപിടിക്കാം, ഇത് അറിയാമെങ്കിൽ ഇത് കണ്ടുപിടിക്കാം. ഓക്കെ, ഇങ്ങനെ ഒരു, if I know the moment of inertia of this disk about an axis like this, I can find out moment of inertia of the same disk about an axis passing through the tangent. ഇങ്ങനെ കണ്ടുപിടിക്കാം. അതെന്താ? അത് പാരലൽ ആക്സിസ് അപ്ലൈ ചെയ്താൽ മതി. ഓക്കെ, സോ ഐ ഹാവ് പാരലൽ ആക്സിസ് ഹിയർ. ഇത് അപ്ലൈ ചെയ്യാം. അപ്പോൾ പെർപെൻഡിക്കുലർ ആക്സിസ്, പാരലൽ ആക്സിസ്, ഇവിടെ അവിടെ എന്ത് വേണേലും നമുക്ക് applying those two theorems we can find out. So we will consider another axis. Okay, now we are going to find out the moment of inertia of the disk about a diameter. So what is a diameter? We have already found out this one. Now I am going to find out about a diameter, means about an axis passing like this as well as this. So I will draw the figure. So I have this one. This I have already found out this one passing through the center. This is about PQ. Then I have already found out this to be mr squared by 2. Okay. Now I want to find out the moment of inertia of this disk about two diameters. That is, I am considering two diameters like this. Say AB. As you know, it is one diameter. Another diameter I can consider is like this, passing through the center. It is CD. So just like we have done in the case of a ring, I can say that if I know this one, I can find out this one or this one by applying perpendicular axis here. So you are already familiar with that. So I can write here mi about PQ is equal to mi about AB plus mi about CD. So this is what perpendicular axis theorem states. Mi about this axis is equal to sum of moment of inertia about this axis plus this axis. Also, you should note that mi about AB, I'm using short form, sorry for that. Mi about AB is equal to mi about CD. Okay, they are two equal one. And now we have already found out this to be mr squared by 2. So what is that? I am taking this to be I. Suppose I am taking each of these moments of inertia to be I can say that mi about P2. I have already taken derived it to be mr squared by 2. So I can say that mr squared by 2 is equal to. So that is this quantity is equal to each of this thing is I. So I can say I plus I. So here I am taking moment of inertia of the disk about this one as I, about this one also as I. I plus I will give you this one because they are equal. I plus I is equal to mr squared by 2 means this I should be mr squared by 4. So this is what we are getting. So what is your finally I can say that if I am taking a disk like this, moment of inertia of the disk about this axis passing through the center perpendicular to the plane is mr squared by 2. About this axis, that is about one diameter is mr squared by 4. About another axis is mr squared by 4. അത് ഇങ്ങനെ ഏതെങ്കിലും ആക്സിസ് എടുത്താലും അത് mr squared by 4 ആയിരിക്കും. So applying like this, if this is mr squared by 4, what will be this one about a tangent? അത് നമുക്ക് കണ്ടുപിടിക്കാം. Just apply parallel axis theorem. Parallel axis theorem എന്ന് പറഞ്ഞാൽ this plus m into r squared will give you this one. So it will be mr squared by 4 plus mr squared. അപ്പോൾ അത് നിങ്ങൾ കാൽക്കുലേറ്റ് ചെയ്ത് കഴിഞ്ഞാൽ നിങ്ങൾക്ക് കണ്ടുപിടിക്കാം. So if you know the moment of inertia of an object about a particular axis, we can find out the moment of inertia of the body about any other axis by applying any of the theorems, that is parallel axis theorem and perpendicular axis theorem. അപ്പോൾ ഇത്രയും കാര്യങ്ങൾ now we have covered moment of inertia of a rod, moment of inertia of a ring and moment of inertia of a disk. The next topic is moment of inertia of a solid cylinder. അപ്പോൾ എല്ലാ കാര്യത്തിലും നമ്മൾ ചെയ്യുന്നത് വെച്ചാൽ we will consider a body, the body for which we have to determine the moment of inertia. We will consider that what this body is made up of. അത് നോക്കിയിട്ടാണ് നമ്മൾ ചെയ്യുന്നത്. ഇപ്പോൾ ഒരു സ്കെയിൽ എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ അത് ഇറ്റ് ഈസ് മെയ്ഡ് അപ്പ് ഓഫ് സ്മോൾ എലിമെന്റ്സ്. ഓക്കെ, റിംഗ് എന്ന് പറഞ്ഞാൽ അത് നമ്മൾ ഓരോ സ്ട്രിപ്പായിട്ടാണ് ഫോം ചെയ്യുന്നത്. ഓക്കെ, ഡിസ്ക് ആകുമ്പോൾ നമ്മൾ റിംഗിൽ നിന്നാണ് ഫോം ചെയ്യുന്നത്. സോ വിൽ ഫസ്റ്റ് കൺസിഡർ വാട്ട് ദ ബോഡി ഈസ് മെയ്ഡ് അപ്പ് ഓഫ്. എന്നിട്ട് ആ ഒരു സ്മോൾ എലിമെന്റിന്റെ മാസ് എടുക്കുക, അതിന്റെ മൊമെന്റ് ഓഫ് എനർജി എടുക്കുക, ഇന്റഗ്രേറ്റ് ചെയ്യുക. അതാണ് നമ്മൾ ചെയ്യുന്നത്. അപ്പൊ അടുത്ത നമ്മൾ കൺസിഡർ ചെയ്യാൻ പോകുന്നത് ഒരു സോളിഡ് സിലിണ്ടർ ആണ്. സോളിഡ് സിലിണ്ടർ കൺസിഡർ ചെയ്യുമ്പോൾ we will see that if you take a solid cylinder, you can say that this solid cylinder is made up of a large number of discs. അടുത്ത വെർഷനാണ്. അപ്പോൾ പല 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 ഡിസ്ക് ചേർന്നിട്ടാണ് ഒരു സോളിഡ് സിലിണ്ടർ ഉണ്ടായിരിക്കുന്നത്. അതുപോലെ തന്നെ നമുക്ക് ഒരു ഹോളോ സിലിണ്ടർ വേണേൽ കൺസിഡർ ചെയ്യാം. ഹോളോ സിലിണ്ടർ എന്ന് പറഞ്ഞാൽ എങ്ങനെ ആയിരിക്കും ഉണ്ടായിരിക്കുന്നത്? ഹോളോ സിലിണ്ടർ വിൽ ബി മെയ്ഡ് അപ്പ് ഓഫ് എ ലാർജ് നമ്പർ ഓഫ് റിംഗ്സ്. അങ്ങനെ ആയിരിക്കും. സോ യു ക്യാൻ ഇമാജിൻ any body, if you are considering, how is it made up of, what are the constituents that are making up the given body. എന്നിട്ടാണ് നമ്മൾ അതിനെ ഒരു പർട്ടിക്കുലർ സ്ട്രിപ്പോ അല്ലെങ്കിൽ ചെറിയൊരു എലിമെന്റോ കൺസിഡർ ചെയ്യുന്നു, അതിന്റെ മാസ് എടുക്കുന്നു, അതിന്റെ മൊമെന്റ് ഓഫ് ഇനർഷ്യ നോക്കുന്നു. If the different strips or different elements are at different distances from the axis that we are considering, we will integrate it, then we will get the result. അങ്ങനെയാണ് നമ്മൾ പ്രൊസീഡ് ചെയ്യുന്നത്. So our next topic is to determine the moment of inertia of a solid cylinder. Okay. So our next topic is to find out the moment of inertia of a solid cylinder. And the axis that we are first going to take is an axis passing through the center and perpendicular to its length. So അങ്ങനെയാണ്. ഇപ്പോൾ ഇതൊരു solid cylinder. So here we have a solid cylinder like this. Actually this is a hollow cylinder. I said just because we have two lids here. അതുകൊണ്ട് നമുക്ക് പുറമേ നോക്കുമ്പോൾ when I am looking from outside, we will feel that it's a solid cylinder. Okay, so the axis that we are considering first is about an axis through the center and perpendicular to its length. അങ്ങനെയാണ് വരിക. So I have drawn this. I have taken the radius of the solid cylinder as capital R. Then total length of the solid cylinder as small l. And this is an axis passing through the center. That is AB. Is an axis passing through the center. this much length is L by 2 and this much length is L by 2. Okay. അപ്പോൾ ഇതാണ് എൻ്റെ ഒരു ആൻഡ് ക്യാപിറ്റൽ എം ഈസ് എ മാസ് ഓഫ് ദി സോളിഡ് സിലിണ്ടർ. അപ്പോൾ ഇത്രയും കാര്യങ്ങളാണ് ആദ്യം നമ്മൾ എടുക്കുന്നത്. സോ ഫോർ ഡിറ്റർമിനിങ് ദി എം ഐ ഓഫ് ദ സോളിഡ് സിലിണ്ടർ അബൌട്ട് ദിസ് ആക്സിസ്, ഫസ്റ്റ് വിൽ കൺസിഡർ ഹൗ ഇറ്റ് ഈസ് മെയ്ഡ് അപ്പ് ഓഫ്. ഒരു സോളിഡ് സിലിണ്ടർ എന്ന് പറഞ്ഞാൽ വി ക്യാൻ കൺസിഡർ ദാറ്റ് ഇറ്റ് ഈസ് മെയ്ഡ് അപ്പ് ഓഫ് എ ലാർജ് നമ്പർ ഓഫ് ഡിസ്ക്സ്. ഇപ്പോൾ അതുപോലെ ഒരു ഡിസ്ക് ആണ്, ജസ്റ്റ് ലൈക്ക് വി സേ ഇപ്പോൾ ഈ സോളിഡ് സിലിണ്ടർ ആണെങ്കിൽ ഇതിന്റെ ഒരു ഭാഗം, ഇഫ് ഐ കട്ട് ദിസ് വൺ, യു ക്യാൻ സീ ദാറ്റ് ദിസ് വിൽ ബി ഇൻ ദ ഫോം ഓഫ് എ disk. For example, this one, this one is a disk. Here also I have a disk. So I can say that this solid cylinder, if it is a disk, I can say that this solid cylinder is made up of a large number of disks. ഇവിടെ തൊട്ട് ഒരു ഡിസ്ക് ഇവിടെ, ഒരു ഡിസ്ക് ഇവിടെ, ഒരു ഡിസ്ക് ഇവിടെ, like that. If I am having a number of disks from this point to this point, അപ്പോൾ ആ ലിമിറ്റ് ഒക്കെ നമുക്ക് ഓൾറെഡി കിട്ടി. അതായത് I will be taking, when integrating, I will be taking the limit from minus L by, this will be taken as 0, just like in the case of what we are taken for a rod അല്ലെങ്കിൽ bar, അതെടുത്ത പോലെ തന്നെ this point will consider as 0, this point as minus L by 2, ഇവിടുന്ന് L by 2, ഇവിടുന്ന് അങ്ങോട്ട് L by 2. So this point is minus L by 2, this is 0, this is plus L by 2. So such disk can exist from here to here. That is, when I am integrating, I will integrate from minus L by 2 to plus L by 2. So we can see that this solid cylinder is made up of a large number of disks lying between minus L by 2 to plus L by 2. അങ്ങനെയാണ് നമ്മൾ ചെയ്യാൻ പോകുന്നത്. So our procedure is like what we have done earlier. That is, we will consider that the solid cylinder is made up of a large number of disks. We will first find the moment of inertia of a small disk. ഒരു ഡിസ്കിൻ്റെ കണ്ടുപിടിക്കും. എന്നിട്ട് we will say that it lies from this point to this point, then we will integrate. So for that, first quantity that we will take is mass per unit length of the solid cylinder. Then we will proceed like that. അപ്പോൾ ഇവിടെ I have considered a disk which is at a distance of x from the central axis. The radius of the disk is same as the radius of the solid cylinder. അതായിരിക്കുമല്ലോ this much. The thickness of the disk is dx and this is situated at a distance x from. So CD is an axis passing through the center of the disk and passing through the center but lying in its plane. അപ്പോൾ അതായത് നിങ്ങൾ ആലോചിക്കേണ്ടത് ഇങ്ങനെയാണ്. If I am considering this as this somewhere here, so this is a solid cylinder. This is a portion of the solid cylinder, a disk which is lying somewhere here at a distance x from the central axis. Central axis എങ്ങനെയാണ്? I can show you. Different axes are possible. One axis I will take is like this. I can take this axis. The axis which I have taken now is this one. Okay, ഇങ്ങനെ ഇറങ്ങാലോ. So this is an axis passing through this one. So I am considering a disk somewhere here at a distance x from this one. I will find the mass of this disk. Find the moment of inertia of this disk about this axis. അത് കണ്ടുപിടിക്കുക. എന്നിട്ട് ഇതിനെ ഇന്റഗ്രേറ്റ് ചെയ്യുക ഇവിടെ തൊട്ട് ഇവിടെ വരെ. So we will say that this solid cylinder is made up of a large number of disks and will integrate. അപ്പോൾ ആദ്യം ചെയ്യേണ്ട ഇതാണ്. So we have an axis passing the center. We can rotate like this. Okay. We can have another axis that we will take later. Anyway, I will just show you. We can have different axes. We can have an axis passing through the center perpendicular to this one. So what will it look like? ഇങ്ങനെ ഉണ്ടാക്കാം. Like this we can pass the center from here to here. I can pass like this. Then I can rotate like this. Okay. ഇങ്ങനെ ഉണ്ടാക്കാം അല്ലേ? Just to show you. ഇങ്ങനെ നമുക്ക് ഇറക്കാമല്ലോ. ഇങ്ങനെ ഇറക്കാം. So this is also an axis passing through the center but perpendicular to the, I mean parallel to the length, ഇങ്ങനെ വരാം. അപ്പോൾ അങ്ങനെ പല axes we can consider. Now we are considering this axis. Okay, so first we have to consider the mass per unit length of the, so that is our first step. First we will consider the mass per unit length of the cylinder. We will take, then you will take the mass of this particular disk, small disk we will take. Then we will calculate the moment of inertia of this disk about this axis. But you have to remember that this is a disk. This is an axis passing like this. That means we have already derived expression for the moment of inertia of a disk about this axis. This is the diameter, that we have already derived as mr squared by 4. Hope you remember that. ഇത് നമ്മൾ കണ്ടുപിടിക്കും. This was if I am considering a disk like this, about this axis it is mr squared by 2, about this axis it is mr squared by 4. അപ്പോൾ അതാണ് ഇവിടെ കിട്ടുന്നത്. ഇവിടെ സെയിം ലൈക്ക് ദിസ്, ഇഫ് ഐ ഹാവ് എ ഡിസ്ക് ലൈക്ക് ദിസ്, അബൌട്ട് ദിസ് ആക്സിസ് പാസിംഗ് ആസ് എ ഡയമീറ്റർ, ദിസ് വൺ വി ഹാവ് ഓൾറെഡി കാൽക്കുലേറ്റഡ് ആസ് mr squared by 4. അത് വെച്ചുകൊണ്ട് ഇത് കണ്ടുപിടിക്കണം. സോ ഫ്രം ദിസ് വൺ ഐ ക്യാൻ ഫൈൻഡ് ഔട്ട് ദിസ് വൺ. ഹൗ ഐ വിൽ ഫൈൻഡ് ഔട്ട്? ബൈ അപ്ലൈയിങ് parallel axis theorem. So our procedure is like this. We will first consider that this solid cylinder is made up of a large number of discs. We will consider such a disk at a distance x from the axis that we are considering, and we have taken the length of the strip path dx. We will first calculate mass per unit length, then we will find the mass of this strip. From the mass of this strip we will calculate the moment of inertia of this disk about CD. After getting moment of inertia about CD, we will calculate moment of inertia of this strip along about AB. കണ്ടുപിടിക്കും. അത് കഴിഞ്ഞിട്ട് we will say that this disk is made up of a large number of disks. Then we will integrate the expression that we are getting at that point of time. അങ്ങനെയാണ് നമ്മൾ ഈ full essay പോകുന്നത്. So the first step that I will write here is mass per unit length of the cylinder. Mass per unit length of the cylinder is equal to, what is mass per unit length? This is total mass is m, total length is L. So I can write m by L. Usually take area or volume, but here it is easy to take mass per unit length because I can multiply by this length. This is the length of this strip which is dx itself. ശരിക്കും thickness of the disk ആണ്. അത് ഇവിടെ നമുക്ക് ലെങ്ത് ആയിട്ട് എടുക്കാം because this is considered as length. This much distance is actually the length of this strip. So from that strip I can take the mass. So next step is mass of the disk. Therefore mass of the disk is, this quantity is taken as rho. Okay, this I forgot to write here. This can be taken as rho, that is m by L. This is a particular quantity which we have studied as linear density. Density is mass by volume. Mass per unit length is a quantity which is known in physics as linear density. അതുകൊണ്ട് എഴുതിയെന്നുള്ളൂ. You might have I don't know whether you have studied melty string എന്ന് പറഞ്ഞൊരു ഫിസിക്സിൽ ഒരു എക്സ്പീരിയൻസ് ഉണ്ട്. അപ്പോൾ അതിനകത്ത് നമ്മൾ കൺസിഡർ ചെയ്യുന്നതാണ്, we have a string which is vibrating and we will take the one constant to be put in that experiment as linear density, that is rho. Okay, mass of the disk is per unit length. Mass per unit length we have length of this disk is nothing but dx. So here it is dx, so I can write rho into dx. So it can be written as m by L into dx. So this is a mass of the disk. After getting mass of the disk, we will go for the moment of inertia of the disk about this diameter. So what is that? About its own diameter. Therefore mi of the disk about its own diameter, that is diameter another CD, right? CD, about this diameter will be equal to, that we have already studied that if you are taking a disk, the moment of inertia of the disk will be mass into radius squared divided by 4. Okay, mass into radius squared by 4. So we have studied that mi of a disk about one of the diameters. So that is this one. This is the diameter. About this diameter is mass into radius squared by 4. What is the mass of this disk? Mass of the disk is this one. Radius normally is the same as this one. Radius is same as the radius of the solid cylinder, and that divided by 4. So this will give you mass, that is m by L dx into radius squared, that is r squared divided by 4. So that is the moment of inertia of this disk about this axis. After getting this one, you can find out this one. What is the moment of inertia of this disk about AB? Just apply parallel axis theorem. So that is our next step. So this will be m by L, so it will be like this. Okay, then moment of inertia of the disk about AB. Moment of inertia of the disk about AB. So for doing this, you apply parallel axis here. And then moment of inertia about CD plus mass into this distance. So that is equal to mi about CD plus mass into distance squared. That is equal to mi about CD is this one. That is m by L dx r squared by 4 plus what is mass? Mass of this one is m by L into dx. M by L into dx into distance squared into distance between these two axes is x, that is x squared. So after simplifying this, we will be getting mi of the disk about AB, mi of this disk about AB. അത് കിട്ടിക്കഴിഞ്ഞാൽ after that we can integrate from this point to this point, because such disk will be coming from this point to this point. Like that we can. Now I can say that moment of inertia of the cylinder about AB is equal to sum of moments of inertia of all disks lying between minus L by 2 and plus L. So what we are going to do is integrating from this point to this point, moment of inertia of all these disks lying between minus L by 2 and plus L by 2. Then I will get the moment of inertia of the whole solid cylinder about this axis. That is what we are going to do. So sum of moment of inertia of all disks lying between minus L by 2 and plus L by 2, integrating that. So I will be obtained as minus L by 2 to plus L by 2. Our first here was m by L. So for easiness, I am just taking, instead of m by L, you can take rho. For easiness in writing, otherwise you will have to write everywhere m by L and all that. So from that equation, I will take minus L by 2 to plus L by 2 of rho r squared. Instead of m by L squared, I will rho r squared dx by 4 plus minus L by 2 to plus L by 2. What is the second one? The second one is rho x squared dx. Okay. Rho r squared x dx by 4 plus this one. Okay. This is what we are going to write. So moment of inertia of the cylinder about AB that we are getting, that is I is equal to, the rho is a constant. Rho is equal to mass of the cylinder by length of the cylinder. It is a constant. Radius of the cylinder is a constant. 4 is a constant. Here rho is a constant. Okay. So all constant can be taken outside. So I will get rho r squared by 4 integral minus L by 2 to plus L by 2. Here the remaining is only dx plus the constant here is rho minus L by 2 to plus L by 2 x squared dx. So this is what we are going to do. Now we know that the integral of dx is x. Then you apply limit. Integral of x squared dx is x cubed by 3. Apply the limits. Then you will get the equation what we are looking for. Okay. So this is rho r squared by 4 integrating dx x minus L by 2 plus L by 2 plus rho into x squared dx integral is x cubed by 3, then apply limits minus L by 2 to plus L by 2. And we have to apply here one rule, that when you are integrating from minus L by 2 to plus L by 2, it can be written as 2 into 0 to L by 2, because we know that it is that one rule in integration. So we will just apply that. So this equation can be rewritten as I is equal to, I am changing this, so writing rho r squared by 4, then I limit I am changing from 0 to L by 2 for our easiness. 0 to L by 2 limit I have to put here 1 2. So this minus L by 2 to plus L by 2 limit can be changed to 0 to L by 2 for easiness, just by putting 1 2 here. So I can write 2 into, now x here, it can be 0 to L by 2 plus then rho into, again here I am changing the limit. I will put here 1 2, rho into 2 into x cube by 3, limit I will change to 0 to L by 2. So that will be easy for us. So this will become rho r, this will become rho r squared by 2 2 and this one you will get 2. Then you can apply limit here. Okay. Then you will have x only here. Apply upper limit. Lower limit applied because 0. So L by 2 plus 2 rho into, instead of x I will apply the upper limit. L by 2 the whole cube. Okay. L by 2 the whole cube by 3. Okay. So this is what we are getting after applying the limits. So this is rho r squared by 2, rho r squared L, okay, rho r squared L by 4 plus, what is this one? This is 2 rho, this is L cube by 8 by 3. So it will be L cube by 24. Here is 1, 2. So it will be 12. So that is rho L cube by 12. So this is what we are getting. Now we can substitute for this rho. So what is rho? Rho is m by L. Okay. So I can put here. Rho is nothing but linear density. The mass per unit length. So I can write here. Rho is m by L. So I can write m by L r squared L by 4 plus m by L L cube by 12. So this will be, this L and L will get cancelled. I will get mr squared by 4. So that is nothing but I is equal to mr squared by 4 plus ml squared by 12. That is what we are. Mr squared by 4 plus ml squared by 12. So I can write this as, finally m is constant. So I can take it out, the common one. I will get it as mi is equal to m into r squared by 4 plus L squared by 12. So this is the moment of inertia of a solid cylinder about an axis passing through the center perpendicular to. So so what we are getting is this one. Okay. So I have a solid cylinder, like a solid cylinder. The moment of inertia of this solid cylinder about this axis is given by m r squared by 4, where m is the mass of the solid cylinder, r is the radius of the solid cylinder, L is the length of the solid cylinder. So this is what we are going to get. And then we may be remembering like this. We got the moment of inertia of a rod about an axis passing through the center as ml squared by 12. The equation of, in this equation, if you take r to be 0, what will you get? You will get, this day will be 0, it will be ml squared by 12, which is same as the moment of inertia of a rod. This is a solid cylinder. If I take r to be 0, this radius will reduce to 0. Radius is 0 at radius, what we are getting is a rod. So if this radius is getting reduced to 0, what we will be getting? A rod. So then we will arrive at the moment of inertia of a rod. Just by putting r is equal to 0, we will have ml squared by 12. That means the solid cylinder will reduce to that of a rod. We will be getting ml squared by 12. Now the second axis that we are considering for determining the moment of inertia is an axis passing like this through the cylinder like this. So what is the peculiarity of this axis? This axis is actually the axis of the cylinder itself. Earlier we were considering this axis, right, perpendicular to this one, okay, length. Now we are considering one axis which is parallel to the length, or it is the axis of the cylinder. Here what we have to assume is that this cylinder, as we have considered earlier, it is made up of a large number of discs. Now I can consider that it is made up of a large number, one disc like this, another disc like this, another disc like very thin discs, one placed one over the other. Okay. What is the difference it has with this one? Here one disc was here, just like this. So we can say that this is made up of a large number of discs. One such disc is here. This is one disc. Okay. So we have disc like this, one here, another here, like this. So we have one disc, placed on that we have another disc. So these are placed on one on top of the other. But sideways on. So the difference between these two things is here as well as here the cylinder is made up of disc, but here it is placed side by side, side in side വെച്ചിട്ട് from minus L by 2 to plus L by 2 they are placed. Here you can see that it is placed one on the top of the other. Also you can see that these different discs are at different distances from the axis AB. Either this is at a distance x. If I am considering another disc here, it will be at another distance from the axis. പക്ഷേ ഇവിടെ അങ്ങനെയല്ല. Here all the discs are having the same radius. Okay? All the discs are about a particular axis, common axis under. So I can consider that this solid cylinder is made up of a large number of discs. Suppose the mass of each disc is smaller, the radius of each one, എല്ലാത്തിനും common radius ആണ്. So what you have to do is to find the moment of inertia of the cylinder about this axis. First of all, you have to take the moment of inertia of each of the discs about a particular axis, about this axis passing through the center. So we have already studied that if I have a disc like this, if I have an axis passing like this, suppose it is AB, I am taking only one element here, one disc out of these, all these discs I am taking here. The moment of inertia about this one is given by mr squared by 2, where m is the mass of the disc and r is the radius of the disc. So this is the case for a single disc. ഒരു ഡിസ്കിന്റെ ഇതേ ആക്സിസ് ഇതിൽ ഒരെണ്ണം മാത്രം ഇങ്ങോട്ട് എടുത്തു കഴിഞ്ഞാൽ the moment of inertia about that axis is mr squared by 2. അങ്ങനെ കുറേ ഡിസ്കുകൾ ഉണ്ട് ഇവിടെ. So we have such similar disc one on top of the other. ഇവിടെ നമുക്ക് ഇന്റഗ്രേഷന്റെ ആവശ്യമില്ല. Integration is when different discs are at different distances from the axis. But here we can see that all the discs have a common same radius. So there is no need for integration. What we have to do is we have to take the moment of inertia of each disc, then just sum it up. So that is what we are going to do to find out this one. So you know that this is the equation for a moment of inertia of each disc. So I can write the first equation as moment of inertia of each disc about AB is equal to m into r squared divided by 2. So we have already studied m r squared by 2. Since here is a mass of each disc is m r squared by 2. Therefore next step is mi of cylinder about AB, that is I can be written to be equal to sigma mr squared by 2. Just summing up the moments of inertia, this one moment of inertia of this disc plus this one plus this one plus this one plus this one, all the things you have to add. So adding all these things, I can write here, this can be written as, what is sigma m? M എന്ന് പറഞ്ഞാൽ it is the mass of a single disc. ഒരു ഡിസ്കിന്റെ മാത്രമാണ്. സിഗ്മ എം മീൻസ് യു ആർ ആഡിങ് ദിസ് മാസ് പ്ലസ് ദിസ് മാസ് പ്ലസ് ദിസ് മാസ് പ്ലസ് ദിസ് മാസ് എല്ലാം കൂടെ കൂട്ടുകയാണ്. ആഡിങ് ദ മാസസ് ഓഫ് ഓൾ ദ സ്മോൾ ഡിസ്ക്, യു വിൽ ഗെറ്റ് ദി ടോട്ടൽ മാസ് ഓഫ് ദി സിലിണ്ടർ. ഓക്കെ, then sigma m can be written as m. Therefore this I can be written as I is equal to mr squared by 2. So this is what we are getting. So we can say that this equation is same as the moment of inertia of a disc. അപ്പോൾ moment of inertia of a disc എടുത്തു കഴിഞ്ഞാൽ about this axis it will be mr squared by 2. Okay, mr squared by 2, and if I take the whole cylinder also it is mr squared by 2. അവിടെ എവിടെയാ വ്യത്യാസം? m എന്ന് പറഞ്ഞാൽ ഇതിന്റെ കേസിലാണ് ഇതിന്റെ മാസാണ്, the mass of this disc alone. When I am considering the solid cylinder, I will have a situation like this where the equation is same mr squared by 2, but m means it is the mass of the whole cylinder. So we can say that moment of inertia of a disc about this axis is same as moment of inertia. The only thing is that the mass is equation is same, but that mass involved in the equation is different. Here m is the mass of the cylinder, here it is the mass of a single disc. So now we have covered the moments of inertia of a rod, then a ring, a disc, then a solid cylinder. So ഇത്രയും കാര്യങ്ങൾ moments of inertia derivation we have already covered. The one thing which is remaining now is a moment of inertia of a sphere. So there also we will consider that a sphere is consisting of different discs. അപ്പോൾ നമ്മൾ എന്ത് ചെയ്താലും അതിനെ സ്പ്ലിറ്റ് ചെയ്തിട്ട് നമ്മൾ അതിനെ moment of inertia due to each constituent we will find, then we will integrate. So that is what we are going to do. Okay, thank you.